Hey there, AP Calculus BC Intrepid Explorers. We are back on the polar calculus train, except still no calculus today. We actually have a couple more days of no calculus. We want to make sure you feel extremely confident on your polar equations before we get to the calculus part of this. Today we are going to really just focus on bringing in what we learned at the end of last class, converting between polar and rectangular coordinates, and apply that to equations, because it's all fine and dandy to figure out how to find one point in two different ways. But what we're going to look at today is how can we find and create a graph using our two different types of equations. We're just going to start with rectangular equations, our x's and y's, and figure out how to create them in polar. And then we're going to go vice versa, and we're going to do our polar equations and figure out how to create them using rectangular ones. This should be a much quicker video than last class, I hope, but we haven't gone through it yet, so who knows. All right, let's begin. On this one, we're going to start with rectangular, and I have a graph type next to it because we should know what all of these graph types are. So we're both going to name the type of equation and also sketch a quick graph just to make sure we remember how to do that. So y equals 4. What type of graph does that make? I think it makes a horizontal line, doesn't it? And if we wanted to graph that, nothing too terrible. Right, we just need to make sure our y-axis goes up to 4. Looking good, and we have our horizontal line straight across. Okay, so what are we doing for polar then? Well, somehow for polar we're going to need to create a straight line, which is kind of weird if you think about it, because ultimately what that means is we have to turn some amount and then go some amount out and land on that line. And then we have to turn a little bit further, go some amount out, and land on that line. And those two are actually going to be a little bit trickier, we'll find, for linear equations than rectangular equations are. So how do we do this? Well, we need to keep in mind our three main formulas that we learned last class. And I'll remind you of them down below. We learned that x was equal to r cosine of theta. We learned also that y was equal to r sine of theta. And I guess there are technically two more. We learned that x squared plus y squared was equal to the radius squared. And last but not least, that if you took tangent of theta, it was equal to the opposite over the adjacent. Using combinations of those four, we're going to be able to go through and replace the variables in here with only r and theta. Because ultimately, what makes an equation rectangular is it's an equation that either contains x or y or some combination of x and y and no other variables. Something that our definition maybe of our polar equation is that it's an equation that contains theta or r or some combination of r and theta and no other variables. So currently this equation is not polar because it has no combination of r and or theta. So to do that, we need to somehow replace y with only combinations of r and theta. And luckily we have this wonderful relation down below. And it tells us that anywhere we see a y, we can replace it with r times the sine of theta. Of course, everything else stays the same, equals 4. And I'm going to box that off. Great. Are we done? Well, not really. Technically, this is the right polar form, and if you plug this into a graphing calculator, some of them will be able to graph that no problem. However, just like we like to write our equations in the terms of y equals f of x, we also, maybe I should do that down here, we also like to write our polar equations as r equals f of theta, r equals some function of theta, which means r is isolated. Luckily, I think isolating r here is nothing terrible. We just divide sine of theta and end up with 4 divided by the sine of theta. Okay. Do we have to memorize that this graph makes a rectangular equation, and in particular a line? No, but if you can, you'll start seeing some connections, realizing that if we have a pattern of some value 4, which actually ends up being our y-intercept, I wonder if it's always that, and then dividing by sine of theta gave us that horizontal line, right? Sine is the y. It might help you recognize a few of these graphs. Okay, so keep that in mind. We'll come back to that fact in a second. We're on to part B. X squared plus y squared equals 25. We should recognize that as a circle. In particular, h and k for our circle, because it's x minus h squared plus y minus k squared equals, and maybe I'll write that out, x minus 0 squared plus y minus 0 squared equals the radius squared, right? That's our 0, 0, so our center then is 0, 0, and our radius is 5. So we center the circle at 0, 0. You can put a point there, but technically there isn't that point on your graph. And then we have a radius of 5. So we go out to 5, and I have learned in the past when we create circles that you make the circle first, and then you do the tick marks after. So here is my circle. That was somewhat decent. And then we go out 5. 1, 2, 3, 4, 5, and you just make it fit. If you try to do the tick marks first, unless you're using a ruler and a compass, your circle is going to look real not circle-y. There we go. Great. We have our circle, radius of 5, centered at 0, 0. How do we do this in our polar form? Well, it seems to me polar form-wise, this would be actually a lot easier to create because you rotate some amount, and then by definition of a circle, we're just going out 5. That's the radius of my circle. And I could rotate further and still go out 5, and rotate further and still go out 5. It seems like r is pretty constant here, and theta is what's changing. So if we create this equation, then we're going to take our x squared plus y squared equals 25. Hopefully recognize x squared plus y squared as the same thing as r squared. Right? We saw that down below over here. And then the equals 25 doesn't change. And then we finish isolating r. Square root both sides. You can put the plus minus square root if you would like, but it turns out that that is unnecessary, but I'll explain why right now. Our final equation for a circle is r equals 5. That is a really easy equation. In fact, I would argue it's probably easier than this. Why is it r equals 5? Well, if you made a quick table, input, comma, output, and you just picked a whole bunch of different thetas, because theta isn't in this equation, it's not dependent on anything, r is going to be 5 every time. So maybe we could pick theta is like, I don't know, pi over 4. Yeah, let's just do a lot of pi's over 4s. 3 pi over 4, 5 pi over 4, 7 pi over 4. Well, look what we get up here. So we turn pi over 4, that's right about here, and then we extend out a radius of 5, and we put a point at the end. And then we do the same thing for 3 pi over 4, so we turn over to 3 pi over 4, we extend out a length of 5, put a point on the end. So really, by the fact we can choose anything for theta, it lets us rotate as far as we want, and whatever you pick for theta, you stop there, you go out a length of 5, and put a point that will land on the circle. Now, how come we don't need the negatives involved here? And you can put the plus minus 5 if you'd like. Well, imagine that we had something with some negatives here. Okay, imagine we had negative 5 over here, and we said, we want you to choose, let's do, I don't know, 5 pi over 4. 5 pi over 4 is down here, but then negative 5 means don't go out 5 in the direction we're in, go out the other way. Oh wait, we got there by using a positive 5. And so it turns out that anywhere you can get with a negative 5, you will also get with the positive 5, so why bother doing them twice? It's kind of both the blessing and the curse of polar functions, or polar coordinates, because you can arrive at a polar coordinate in an infinite number of ways. A blessing, because you don't need to deal with the plus minus with r, but a curse, because sometimes that can get a little confusing. Okay, moving on. Third one. This graph type is also linear, and I'm just going to put linear here. It's probably going to be a diagonal line because we have both x and y. Typically, we would isolate y here and put this in slope-intercept form, but it doesn't have to be. It's still linear. Y and x are both to the first power. If you wanted to graph it, there's a few ways to do this, but I will go ahead and isolate y, even though it's kind of gross to do so. So I'm going to leave 3x plus 2 on this side, and then take 1/5 of everything, so we get 3/5 x plus 2/5 equals y, and my graph is going to be a very rough sketch here. It is not going to be beautiful. We'll drop this down a little bit. There we go. If we say that this is 1, 2, 3, and then this one is, we'll go the same direction out here, and so on and so forth. Okay, we have a y-intercept of 2/5, that's right about here, and then the slope says go up 3 over 5, or we could treat the slope as 3/5 over 1. So if I go up 3/5 and over 1, that's actually a nice point over there, that's 1 comma 1. Down 3/5 isn't nearly as nice, and then over 1, something like this though. Doesn't have to be perfect. Cool. There's our linear function. Now we already saw a linear function before. It was horizontal, but it had the sine in the bottom and the y-intercept on the top. So let's see if anything like that happens this time. The process, luckily, is really the same. So we have 3x minus 5y plus 2 equals 0. Let's replace the x with its r cosine of theta, and then replace the y with r sine of theta, plus 2 equals 0. And that is our equation. However, we do want to try to isolate r. I'll do this in a couple steps. Remember, when we have a 3 on the outside of parentheses, you don't distribute to everything inside. It's just multiplication. So 3r cosine of theta minus 5r sine of theta. And I'll move the plus 2 over to the other side. If we're trying to isolate r, but I have 2 terms with it, let's factor out the r. Okay, something like this. And then finish by dividing everything off to the other side. So r equals negative 2 divided by 3 cosine of theta minus 5 sine of theta. Now you might say, whoa, that looks way more complicated than the one up above, but it should be a little more complicated. The one up above was a horizontal line and they only needed sine. This one down here is a diagonal line and they needed both sine and cosine. And also, it might be interesting to look at what happens if you divide these coefficients and if you divide these coefficients and see if they tell you anything about your graph. Hint, hint, that looks like a y-intercept to me. So either way, we end up here, and there's our equation. In fact, I bet using a nice little bit of deduction, you could even tell me the form of a vertical line, right? If using both sine and cosine was diagonal, just sine was horizontal, I bet a just cosine at the bottom will be something vertical. Again, nothing that you have to know, but it's nice to make some connections on polar, something we haven't studied very closely until now. All right, last one. This to me looks like a circle again. In particular, it's our circle with x minus 0 squared plus y minus 2 squared equals 2 squared. We always want to write that like the Pythagorean theorem, something squared plus something squared equals something squared. We have our center at 0 comma positive 2 because it's minus h minus k. We do the opposite of each. And then we know the radius is 2. All right, so let's get this graphed. Our xy axis, we're going 0 comma 2, so that's up the y-axis a little bit. Okay, so the center is at 0, 2, and then the radius is 2 more in that direction. So 0, 2, if you want to see the center, is right here. I'm going to do the circle first. You can see that it's going to curl in and look like that. In fact, you might even recognize that as a graph very, very similar to one we looked at yesterday, one of the very first graphs when we did our polar graphs in reduction, right? It had 1 point at the origin. This is a diameter of 1, 2, 3, 4. So remember that diameter of 4, that'll come into play, and it's along the y-axis. All right, well, how do we get there? Well, this one is a little bit trickier. Okay, so I'm going to rewrite the original problem. X squared plus y minus 2 squared equals 4. I see an x squared, and although you could replace this x with r cosine of theta and the y with r sine of theta, I found it's actually a little bit easier to multiply everything out first. And the reason I'm going to do that is because eventually that will give me an x squared and y squared together, which is very easy to replace with r squared, and takes away some of that squared stuff that happens. So let's do a quick multiplication out. Y squared minus 4y plus 4 equals 4. Maybe subtract off the 4 from both sides too, just so we don't have to worry about that. And then we can start replacing. X squared plus y squared is r squared minus 4, and then we know that y can be replaced with r times the sine of theta equals 0. From here, 2 terms, each term has r, so we're going to factor out the r, Leaves me with r minus 4 sine of theta equals 0. Now, from here, you might be tempted to say, oh, let's just divide all of this to the right side. But then you're going to have all of this get destroyed by the 0 over here. Remember, that's one of our big no-nos in math, right? If I told you, and this is a side note, you don't need to write it, if I said, oh, I have x times x minus 1 equals 0, what is the value of x? You'd say, well, there are two values. X is 0, x is 1. If you divide this to the other side, like so, you just get x equals 0, you've lost a solution. So it's always a no-no to divide 0 by an actual variable because you will generally lose solutions. So instead, ask yourself, how would you solve this equation? Well, you'd use what's called our zero product property. You'd make two equations, each set equal to 0, and then solve. And that's what we'll do here. We'll make two equations, r equals 0 or r minus 4 sine of theta equals 0. One equation's already solved. Our other one is easy enough to just add 4 sine of theta over to the right. So now you might be saying, whoa, 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 whoa. Here you had one equation. When you turn it into polar, you have two. And although kind of yes, really no. It's really kind of that same issue when you had r equals 5 and r equals negative 5. You actually don't need both of these. Let's look at the graph of r equals 0 really quickly. R equals 0 means no matter how far you turn, theta can be anything, the radius has to be 0. So instead of going out some amount, we just put a point at 0. And then you turn further, and then you don't go out at all, and you put the point at 0 again. So r equals 0 is actually just a point. It is a point on the origin. However, we know what the graph of r equals 4 sine of theta is. We saw this last class. R equals 4 sine of theta is a circle, and it goes up 1, 2, 3. It's a diameter of 4, and the full circle looks like that, except more circular and not eggy shaped. But either way, you get the idea. This full circle included the origin point. It includes 0, 0. So do we need both of these equations if this one already includes everything that's in that one? No, we don't. So r equals 0 is just, I don't know, an extra solution that's already counted for. So why use that? This is the only equation that we need. Could you give both? Sure. It's just superfluous, it's extra, it's unnecessary. Redundant. All right. Great. We just practiced converting from polar to rectangular. Nope, vice versa, rectangular to polar. Now we're going to go backwards. How do we do that? Well, first thing we're going to do is we're going to take a look at our equation and realize they only have r and or theta in them, and so we need to replace all of those with sine and cosine. Nope, that's a lie, with x and y. Oof, I'm out of it today. All right, how do we do that? Well, we just do the same thing we did before. Let's keep in mind our 4 formulas up here, and it's just going to be combinations of those. You just have to start looking for patterns. Everything in math is patterns. R sine of theta, oh, we can replace that right away. The r sine of theta is just the same thing as y. Great, that was easy. This is y equals 3. Could we have seen that from the original equation? Yeah, I think so. If you had divided both sides by sine, you'd see that r is divided by sine of theta. We saw that same pattern before up at the top. It made a horizontal line with a y-intercept of 3, and this part made it horizontal. And so from there, you might have been able to recognize that as a horizontal line of y equals 3. Of course, you don't have to recognize that, but we're just showing connections. All right, next one. R equals 2 cosine of theta. This one's tricky. Now, the first thing you should do is look at this and say, oh, I already know how to graph this. We saw this last class. This is a circle with a diameter of 2 that also includes the origin. And it's along the x-axis because it's cosine. So it includes the x-axis, diameter of 2 along it includes the origin along the x-axis. That's what my graph looks like. It's a circle. And we know that circles are those, x minus h squared plus y minus k squared equals blah, blah, blah. But how do we get all that from here? Well, this one's tricky. And what I might realize is that I don't know how to replace cosine, but I do know how to replace r cosine of theta. So why don't we go ahead, and I'll rewrite this and leave some gaps over here. Why don't we go ahead and give each side, because whatever we do to one, we do to the other, an extra r, and see if that gets us anywhere. R squared equals 2r cosine of theta, right? We can move that multiplication anywhere we want. And look how beautifully this worked out now. R squared can, of course, be replaced with x squared plus y squared. And on the other side, r cosine of theta can be replaced with x. This gives us x squared minus 2x plus y squared equals 0. And now you might be saying, whoa, 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 that doesn't fit our HK form. How does that become x minus something squared plus y minus something squared equals the radius squared? You're like, there's a 0 over there. What is this trickery? Well, this is actually our standard form for, we could say, a conic section. You can use this standard form to create parabolas, circles, ellipses, and hyperbolas. We can take a standard form and turn it into HK form, the same way we always have by completing the square. So to complete x squared minus 2x, and this is again is extra for you, the y squared I'm not going to touch because that's already with a square. I think we could probably go through, and actually I should leave a little room here, and say, well, to create a minus 2x, this needs to be a minus 1. Right? And thinking off on the side, okay, x minus 1 squared, that's x squared minus 2x plus 1. Are those two the same? No, this has an extra plus 1, so I think I need a minus 1 now. Those cancel. Now they're the same. That looks good. Cool. And then we have our y minus 0 squared. Don't need to change that at all here. Add the 1 to the other side, and we end up with x minus 1 squared plus y minus 0 squared equals 1 squared. And look at that. We have a center of 1, 0 and a radius of 1. Again, all extra things you're not required to do, though completing the square you do have to know how to do. So that's probably good to remember. But we have time on this video, and you can always skim through this if you don't want it. So it's good to remember to see how to convert. Go us. All right, next one. Theta equals 2 pi over 3. Well, let's go ahead and instead of converting this first, let's get a picture of what this looks like. Theta equals 2 pi over 3. And to do that, I'm just going to make a quick table. So we have our input of theta, we have our output of r, and theta has to be 2 pi over 3 every single time. And I'll do maybe 3 of these down here. Okay, so what does that mean? Well, it means that we're going to be rotating to 2 pi over 3. And don't forget, 2 pi over 3 is kind of right about here. Keep that as a reminder. So, right, 1 pi over 3, 2 pi over 3, 3 pi over 3. It's probably a little higher than to cut into thirds, maybe something like that. There we go. So here is our 2 pi over 3. So they're saying, no matter what, I want you to rotate to 2 pi over 3. Always going to rotate there. But then, it doesn't tell us anything about r, so we can pick anything we want for r. So let's pick 1, 2, and let's do a negative of like negative 3. All right, so 2 pi over 3 comma 1 would mean go here and go out to a distance of 1, which is right about there. Okay, the next one says go here and go out a distance of 2. Okay, so same rotation, but now we're going out 2. And then negative 3 would mean go here, but instead of going out 3 this direction, it's negative, so we go the other direction, 1, 2, 3, right about here. What does it look like those points are falling into? Oh yeah, a diagonal line. And it looks something like this. Now this is pretty fascinating because this is a different way to create a diagonal line, but it shouldn't shock you with polar equations because we know there's different ways to get to points, so there should be different ways to create lines. All right, well, how do we actually turn this into a rectangular equation then? Let's take a peek. If we just have theta, the most common way to do this is to introduce tangent. Why tangent? Well, it's one of our 4 formulas, isn't it? Tangent of theta equals y over x. So let's try that. We're going to go ahead and take the tangent of each side. So tangent of theta is equal to the tangent of 2 pi over 3. Now we can replace tangent of theta. That's y divided by x. That's very nice. And on the right side, tangent of 2 pi over 3 is a value. right? If you want to find tangent of 2 pi over 3, that's 2 pi-ish over 3 here. So let's see, that's 60 degrees, so this is going to be a 60 in here, 30, it's going to be negative x root 3. So let's see, tangent is going to be root 3 over that. I think that's going to be negative root 3. There we go. And if you find tangent a different way using your unit circle, good on you. You need to be able to find that though. And then I think we can isolate y pretty easily, multiply both sides by x, so we get negative square root of 3 times x. Or maybe what we're used to seeing it as, negative square root of 3 times x plus 0, y-intercept, slope. This is a line with an irrational slope. Very interesting. It goes down the square root of 3 over 1 every time. Pretty cool. Let's do a few more. R equals 3 secant of theta. I don't know much about secant, so let's go ahead and rewrite that as 3 times 1 over secant's reciprocal, 1 over cosine. And then actually let's get rid of the cosine. How about we multiply both sides by cosine? R cosine of theta equals 3. Now, from here, that's not bad at all, right? This gives us x equals 3. Cool. 1, 2, 3. Here's x equals 3. Could we have seen that earlier? Yeah, I think so. I think if you put this together over here and you said this is r equals 3 divided by cosine of theta, just like with sine but different, we have our x-intercept now, and this is going to cause our line to go vertical. 2 left. R cosine of theta plus r sine of theta equals 1. Oh, this one looks nice, doesn't it? R cosine of theta, that's x. R sine of theta, that's y, equals 1. And then if you wanted to isolate y, if you prefer seeing it that way, negative x plus 1, slope-intercept form. Start at 1, down 1 over 1, down 1 over 1, and we have our diagonal line. Could we have seen that earlier? Certainly. If you take a look at this and factor out an r from each of these, cosine of theta plus sine of theta, and isolate r, 1 divided by cosine of theta plus sine of theta. Look at that. Isn't that the same format of our diagonal line that we saw up here? A value on top divided by some combination of sine and cosine. You'll notice that cosine was subtracting sine and we ended up with a positive slope here. Could have to do with those coefficients out front too. If we look down below though, right, cosine is adding to sine and we have a negative slope. There's a 1 on top, and notice if you divide those coefficients, look what we come up here. Very exciting. And so it shouldn't shock us. There's that diagonal line. Last but not least, r squared equals 1. We have this no problem. We can replace r squared right away. X squared plus y squared equals 1. That is a circle, right? X minus 0 squared plus y minus 0 squared equals the radius squared. So we're centered at 0, 0 with a radius of 1. Should look something like that. Could we have seen this earlier? Certainly. R squared equals 1. Okay, well, what does that mean? Well, if you think about a table and you think about theta and you think about r being squared then, okay, and it having to equal 1, theta means we can rotate any direction we would like. So pick a couple thetas. Maybe we'll do like pi over 4. Did something like this before, 3 pi over 4, and we'll do 5 pi over 4. R squared equals 1, though. We could actually isolate the r if we wanted by taking the square root of both sides. And as we learned earlier, r doesn't need to be plus minus because all the positives will account for the negatives at some point. So what this really means is that r is just 1 every single time. So if we wanted to graph this, and we didn't have this ahead of time, it would mean rotate somewhere, like to pi over 4, and then go out a radius of 1. Rotate somewhere, let's actually even be bold and rotate to pi over 2 this time, that's right here, and then go out a distance of 1. Rotate out a distance of 1, out a distance of 1, so on and so forth. You get the idea, and we have our brilliant circle centered at 0, 0. All right, we went through a bunch of examples here, and hopefully you skimmed through a bit of that, but if you didn't, that's okay. The last part of today is just some practice problems. So there are 6 rectangular to polar and 6 polar to rectangular. I do have all my solutions posted on Teams as always, so you are welcome to take a peek at those if you need help. If any of my solutions are wrong or you're stuck, as always, reach out and let me know. Thank you for your time. 2 more days of our intro to polar, and then we finally get back to the calculus sort of things. Keep up the great work.